In today's fast-paced digital world, applications need to handle massive amounts of data, scale dynamically, and respond in real time. Traditional architectures often struggle under demands. This is where event-driven architecture EDA steps in. Today, I'll walk you through how EDA enables scalable, resilient, and responsive systems. Let's dive in. In this talk, we will explore the core principles of EDA, discuss its benefits and challenges, and examine real world applications in areas like vehicle tracking and messaging platforms, showcasing how EDA enhances system performance and agility. Now, before we dive deeper, let me introduce myself. Before we go further, a little bit about me. I am Mohammed Rizwan, a passionate software engineer with experience in designing scalable and high performance systems. One of my biggest achievements was developing a real time vehicle tracking system that provides instant geolocation updates, driving behavior analysis, and real time SMS and call alerts. This has significantly improved user experience and operational efficiency. Beyond that, I specialize in performance optimization and cost effective scaling, helping businesses ensure their applications run smoothly and efficiently. Now, let's talk about the key components of EDA. Event driven architecture EDA is a software design pattern that enables system to communicate asynchronously through events instead of direct requests. This approach is particularly useful for building scalable, decoupled, and real-time systems. EDA consists of three key components. Number one is event producers. These are components that generate events when something happens. For example, in an e-commerce system, an event producer could be a user clicking the buy now button that may trigger an event. Two is the event brokers. These act as intermediaries that manage and route events between producers and consumers. Example include message queues like Apache Kafka or cloud-based solutions like Azure Event Grid. Number third are the event consumers. These components listen for and respond to events by triggering actions. For example, in a notification system, an event consumer might send an email or push notification when a new order is placed. So the primary advantage of EDA over traditional synchronous architecture is that it allows for better scalability and resilience. Since components are loosely coupled, they can function independently, reducing bottlenecks and improving performance in high demand systems. Understanding the core principle of EDA helps us see why it's so effective for modern applications. Let's go through the three main principles. The first principle is decoupling components. In traditional system, components are tightly integrated, meaning that if one fails, it can impact the entire system. EDA, however, decouples services, allowing them to operate independently. This reduces system failures and prevents bottleneck. For example, in an e-commerce platform, the payment service and order fulfillment service can operate independently, improving overall reliability. The second is asynchronous communication. Unlike request response models where components must wait for a response, EDA processes events asynchronously. This ensures non-blocking operations, meaning services don't have to wait for others to complete their task before proceeding. A great example is a stock trading platform where price updates are processed instantly without waiting for each individual trade to complete. The third principle is the real-time responsiveness. One of the biggest advantages of EDA is the ability to react instantly to changes in data. Systems built with EDA provide a better user experience by responding in real time to events, such as sending notifications when an item is being installed or updating dashboards with live analytics. This is crucial for industries like finance, healthcare, and logistics, where real time updates are essential. So, by following these principles, EDA enable businesses to build more scalable, responsive, and resilient applications. Now that we have covered the principle, let's look at the key benefits of event-driven architecture. The first benefit is the scalability. EDA allows systems to handle growing workloads dynamically by distributing event processing across multiple services. Unlike monolithic architectures where scaling requires upgrading the entire system, EDA enable horizontal scaling, meaning new instances of the services can be added if required. For example, in a streaming service like Netflix, multiple microservices process different types of user interactions in parallel, improving performance under high traffic loads. The second benefit is flexibility and modularity. Individual services can be modified, deployed, or scaled independently without affecting the entire system. This makes it easier to introduce new features or fix issues without downtime. A good example is e-commerce platform, where order processing, inventory management, and customer notifications can be updated separately. The third benefit is the improved fault tolerance. One of the major advantages of EDA is that components don't directly depend on each other. This means that if one service fails, it won't crash the entire system. Other services can continue functioning as usual. For example, in an airline booking system, even if the payment service is experiencing issues, user can still browse flights and add items to their cart. So, in summary, EDA helps businesses build systems that are scalable, resilient, and adaptable, making it a crucial architecture for modern applications. While event driven architecture offers many advantages, its implementation comes with several challenges. Let's go through some key difficulties organizations face when adopting EDA. The first challenge is the complex event orchestration. Managing the dependencies between events can be challenging, especially in large scale distributed systems, since events are asynchronous. Ensuring the correct sequence of execution and handling dependencies between multiple events can require sophisticated orchestration tools and techniques such as event choreography or saga patterns. The second challenge is the debugging and the tracing issues. So, unlike traditional synchronous architectures where tracing a request is straightforward, debugging in EDA is more complex. Events can be processed at different times and across multiple services, making it difficult to track the flow of data. To address this, organizations distributed tracing tools like OpenTelemetry or JIG to monitor event flows and detect failures. The third challenge is ensuring data consistency. Traditional data-based transactions follow ACID, automacy, consistency, isolation, and durability principles, but EDA often requires eventual consistency instead. This means that data across different services may not be immediately consistent, leading to potential issues if not properly handled. Techniques like idempotent, event processing, event sourcing, and compensating transactions help maintain consistency in an event-driven system. Despite these challenges, EDA remains a powerful approach for building scalable and resilient systems. Organizations that successfully navigate these complexities can unlock significant performance and agility benefits. So, the mitigation strategies use event choreography and event sourcing to manage workflows, implement distributed tracing with tools like OpenTelemetry, uh, use event handlers to prevent duplicate event processing, Let's see a real world example of EDA in action. Imagine a real time vehicle tracking system. The vehicle sends location updates as events. The event broker processes the data and sends it to relevant consumer. If critical conditions are met, alerts are sent via SMS or phone calls. Thanks to EDA, everything happens instantly, improving safety, compliance, and customer engagement. The .NET ecosystem offers strong support for event-driven solutions through a range of powerful tools and services. Microsoft Azure provides cloud-native, event-driven services that streamline event processing and communication. Key tools in .NET ecosystem include Azure Event Grid, an event routing service that simplifies event distribution. Azure Service Bus, a reliable message queuing system for handling asynchronous communication. And Mass Transit are distributed messaging frameworks designed specifically for .NET applications. These tools enable developers to build scalable, responsive, and efficient event-driven architectures. To successfully implement event-driven architecture in .NET applications, we need the right tools to handle event routing, message delivery, and high throughput event streaming. Here are some key tools widely used in .NET ecosystem. The first one is Azure Event Grid. It's a cloud-based event routing service that helps manage event-driven workflows at scale. It enables seamless integration between different Azure services and third-party applications by routing events to the right subscribers. The second is the Azure Service Bus. It's a messaging service that ensures reliable message delivery between distributed components. It support features like message queues, topics, and subscriptions, making it an ideal choice for decoupling services and improving fault tolerance. Third is the Kafka or the RabbitMQ. It's the open source alternatives. So Apache Kafka, it's a distributed event streaming platform that handles real-time event processing at a high scale. It is widely used in big data applications. And the other one was the RabbitMQ. It's a lightweight message broker that supports various messaging patterns, making it a good choice for microservices communication. So by using these tools, developers can efficiently implement event-driven architectures while ensuring scalability, reliability, and real-time processing in their applications. So implementing event-driven architecture effectively requires adopting best practices to ensure system reliability and efficiency. So here are the three key best practices. The first best practice is the event sourcing. Uh, Store all changes as events rather than the current state. This makes it easier to roll back changes and provides a full history for auditing and debugging. It is particularly useful in financial and transactional systems. The second is the eventual consistency. Unlike traditional databases with asset transactions, EDA systems often operate under eventual consistency rather than immediate consistency. This means that some delays in data synchronization may occur, but systems should be designed to handle these delays gracefully. Techniques like compensating transactions and saga pattern help manage consistency in distributed systems. The third is the observability and monitoring. So debugging in EDA can be a complex thing since events are asynchronous and flow through multiple services. Use tracing tools like OpenTelemetry or Jagger to visualize event flows and detect failures early. Logs, metrics, and distributed tracing should be integrated into the system for better visibility. By following all these best practices, organizations can improve system resilience, maintenance, and scalability in their event-driven applications. While EDA offers numerous advantages, cost and performance optimization is crucial for maintaining efficiency. Here are three key strategies. The first is optimize infrastructure by batch processing events when real-time responses are not required. Not all events need to be processed instantly. So by batching non-critical events, systems can reduce compute resource usage and improve cost efficiency. For example, analytics data collection can be processed in batches instead of real time. Number two is to implement auto scaling strategies to ensure efficient resource usage. So auto scaling allows event driven services to adjust based on demand, right? Cloud platforms like Azure Functions or AWS Lambda enable serverless auto scaling, ensuring resources are used optimally. This thing helps handle traffic spikes efficiently while keeping the costs low. And the third is the reduce cost by filtering unnecessary events before they reach event consumers. So not all events need to be processed. Filter out redundant, duplicate, or the events that are not needed in the pipeline early. So event filtering at the broker level, for example, using Kafka topic, partitioning or Azure event rate filters can reduce unnecessary processing and improve system performance. By implementing all these optimizations, businesses can maximize the benefits of EDA while keeping operational costs under control. EDA is continuously evolving and several trends will shape its future. The first is the AI driven processing. AI and machine learning will play a bigger role in event driven systems. Automated event processing will allow systems to make complex decisions in real time without human intervention. For example, AI powered fraud detection can instantly flag suspicious transactions. Number two is serverless EDA for reduced infrastructure overhead. Serverless computing, for example, Azure Functions or AWS Lambda, will further reduce the need for managing infrastructure. This enables businesses to focus on event-driven logic without worrying about the server management. It will improve scalability, cost efficiency, and rapid deployment. And the third, the stronger governance models to manage event sprawl. As organizations adopt EDA, they will need better event management and governance. Without proper governance, uncontrolled event sprawl can lead to performance issues, security risk, and complexity. Even catalogs, schema registries, and monitoring tools will be essential for managing large-scale event-driven systems. EDA is set to redefine how applications handle real-time data and will continue to be a key enabler of automation, scalability, and intelligence in modern systems. To summarize, let's review the key takeaways from our discussion on event-driven architecture. First is the EDA enables real-time, scalable, and resilient applications by allowing systems to process and respond to events efficiently. Number two is decoupling services and leveraging asynchronous processing enhance agility and ensure independent evolution of components. Number third, key tools like Azure Event Grid, Azure Service Bus, Kafka, and RabbitMQ streamline event routing, message handling, and real-time event processing. Best practices such as event sourcing, eventual consistency, and distributed tracing help maintain data integrity, observability, and ease of debugging. Optimizing costs and performance through batch processing, auto scaling, and event filtering ensures that event events remain cost effective and efficient. By following these principles and best practices, businesses can successfully implement EDA to build next generation event driven applications. So, mastering event driven architecture is about more than just scalability. It's about building future ready applications that can handle real time events effectively. So, whether it's real time payment, IoT sensors, vehicle tracking, or fraud detection, EDA ensures that systems remain responsive, fault tolerant, and cost effective. And as technology evolves, companies that embrace EDA stay ahead in innovation and performance. The combination of AI, serverless computing, and governance model will drive the future of event-driven applications. Adopting EDA, businesses can future-proof their architectures, improve user experiences, and unlock new opportunities for automation and intelligence. Finally, thank you for joining me today. I hope this presentation has given you a clear understanding of how event-driven architecture can transform your systems. If you have any questions, feel free to ask. Let's build scalable, responsive, and future-ready systems together.